Hi everyone. So today we're going to do the making change problem. And the gist of this problem is just that we want to make change for an arbitrary input amount of change with the smallest number of coins possible. So we're going to start by thinking about what questions we need to ask the interviewer. So the first thing that I see is that the question doesn't specify what coin system we're using. So I might imagine or assume that we would be using the American coin system. So it's, 1, 5, 10, and 25-cent coins. And let's assume that we're not thinking about dollars and half dollars, but you could include those as well. And that would make this problem fairly simple, but we could also imagine other coin systems, like, for example, 1, 3, and 4. And that might change the problem. So we will ask our interviewer what coin system they actually want us to use, and they may tell us that they want us to use American coins or to use generic coins, but we also want to be able to talk about the differences between these different coin systems and the implications of those. So just to talk about that a little bit right now, if we look at the American coin system, we can come up with a very simple algorithm to get the minimum amount of change. So all we have to say is we have some amount of change x, and then we want to basically do a while loop. And I'm just going to write some pseudocode here, so hopefully that'll be helpful. So while x is greater than 0, you want to just say that x is equal to x minus the largest coin that's smaller than x, right? So that way, each turn we're going to remove as much change as we possibly can. And as a result, we're going to maximize the amount that we're reducing the total each time. And so we're going to minimize the amount of total coins required. So this should make intuitive sense for the most part, but we can look at a coin system like this one we have below, and this method doesn't always work. So let's imagine a case where x equals 6. Now, using our algorithm above, we would say x minus 4, which is equal to x minus 4, which is equal to 2, and then 2 minus 1 is equal to 1, and then 1 minus 1 is equal to 0. So we would get 3 coins, but that's not the right answer, right? Because what we actually want is x minus 3, which is equal to 3, and then 3 minus 3 is equal to 0. So in this case, we get 2 coins. So there's some, we have different implications depending on what coin system we actually choose to use. But let's imagine for this case that our interviewer wants us to use a generic coin system. So we'll take the coin system itself as input from the user. So now that we've come up with an answer to our primary question, we can go ahead and think about how we're actually going to solve this problem. So it was really easy when we were using the American coins, but it's going to get a little more complicated now. So just for simplicity's sake, I'm going to use the American coins as an example because it'll be useful for us to have a coin system for testing our problem and whatnot. But we're going to write this algorithm so it's generalized to any coin system. So let's just go ahead and we're going to create an int array called coins, and that's going to be, I'm mostly just doing this now to keep track of it, but we'll use this in our code later. And there we go. So now we want to think about how we're going to solve the problem. And I'm also going to go ahead and actually just put the boilerplate in for this. So public int change, we'll just call it change, and then we're going to take in an int x, which is going to be our amount of change, and we're going to take in the int array of the coins. And so what I'm going to try and do is see how I can break this down into simpler problems, because just trying to take an arbitrary number and make change for it is not necessarily easy for me to wrap my head around. So I'm going to think about a couple simple examples first and just what those outputs would be. And then, for example, x equals 1, we know that the output is 1. X equals 2, the output is 2. X equals 5, we know that the output is 1. And we keep going. X equals 11, the output is 2. And so on and so forth. And so what I'm thinking in terms of actually an algorithm for solving this, I think I'm going to do this recursively because that's going to allow me to break the big problem down into smaller problems. And yes, I know like recursive stuff kind of sucks, especially, in an interview, and it's a little scary, but it's good for us to practice it. So that's part of why we're doing this now. So I'm going to do this recursively, and I'm going to think about what I actually would want to do in a given case. So let's say that x equals 32, for example. Now I want to figure out how the smallest way to make 32 cents is in number of coins. But remember that I can't just do this I don't know which coins to take out to make the smallest amount of change, because we could be using any coin system. So I can't just take out 25 cents and then go with the remainder of that. So I have to actually try all the different options. So what I want to do is I want to take the minimum of all the different options. So I want to take the minimum of change of 32 minus 25 and change of 32 minus 10 and 32 minus 5 and 32 minus 5 and 32 minus 1. So I'm going to do this within my recursive function, and then by doing that, it's going to take a lot of steps, and we're going to optimize this later because this isn't going to be very efficient. But for now, at least, we're going to go ahead, and this is actually a good technique. If you don't know, you don't necessarily want to try and write the optimal solution right away, and we're not going to do that here. But let your interviewer know that you realize that you're not writing the most optimal solution. Let them know that you're going to write a simpler solution first, and then you can take the time afterwards to optimize it. So let's go ahead, and I'm going to erase some of this stuff just so that we have more room. And when I'm writing recursive functions, I like to start by writing the base case because I want to make sure that I'm not going to end up in some sort of infinite loop because I didn't have any way for my code to terminate. And so I'm going to just write if x equals 0, I'm going to return 0, because obviously if there is no change, then it takes 0 coins to make it. So I'm going to go ahead. I need to go through all the different coins and figure out what the minimum is. So I'm going to create a variable int min, and I'm going to set that equal to x. And the reason I'm saying that equal to x is that I know that the number of coins can't be, we're assuming that there are no coins that are negative or 0 value. So there can't be more coins than, and we're going to assume that they're integer values, obviously. So the most number of coins would be to use all 1-cent coins. So the maximum number of coins is x. So I'm just going to use that here, but you could also use some other, you could use like max int or something like that if you prefer. And now I'm just going to create a for loop, and I'm going to go through all of the different coins and try and find the minimum value for all of the possible coins. So we're just going to do for coin. We're going to do if it's greater than or equal to 0, because if it's equal to 0, that's fine. And in that case, we would just call change of 0, and then that would be our base case. But we don't want it to get less. We want it to get down to 0 without going below 0, because then we're going to miss our base case, which would be equally bad. So by doing x minus coin is greater than or equal to 0, we ensure that we're assuming a coin system that is valid, we're going to, that has, assuming that the change that we're making is possible to be made with the coin system, we're going to reach 0 eventually. So we're gonna just so we're gonna call our function, and then we want to just see if min is greater than c plus 1, right? Because we have just removed a coin by calling this change function. So we want to make sure that we factor that coin into our total sum that we're tabulating. And then min is going to be equal to c plus 1. And that is going to be pretty much it. And then we just need to close this out, and then we're going to return the min value. And so here we have pretty straightforward code so far. And like we do always, we want to test this code. So we're going to use these American coins for this test. And now let's just run through it with x equals, let's go with 32 again. So it doesn't really matter that much. You want to test cases where ideally you want to hit as many of the parts of your code as you can. So you want to do a fairly complete test, but you don't have to do anything crazy. You mostly just want to make sure that, to the best of your knowledge, your code is actually correct. And that's the primary goal here. So we're going to go 32, and 32 is not equal to 0, obviously. And so we're going to set min is going to be equal to 32. And this is going to get a little bit tricky because we have to go down through these stack traces, but just bear with me and I'll explain this as best as I can. But we're going to go so now, and I'll just go ahead and keep track of the variables up here. So coin equals 1. So we're going to, actually I'm going to change the order of this to be reverse order because it's going to make this go a little bit quicker. 10, 5, and 1. And so first coin is going to be equal to 25. And now we're going to come down to our if statement. And so 32 minus 25 is 7, which is greater than 0. So we're going to call change on 7. And that is going to be, so now we have to actually go into that. So change on 7. So now x equals 7. And we're going to come back to here, and x is not equal to 0. And we're going to set min is going to be equal to 7. So min equals 7. And then we're going to come down to here, and we're going to say x minus 25 is negative, so we're going to skip that. X minus 10 is negative, so we're going to skip that. And now x minus 5 is not negative, so we're going to come down to here, and we're going to call change of x minus 5, which is 2. So now x equals 2, and we're almost done because we're just going to have to go through 2 more times. And now x equals 2, min equals 2. I guess I should have here that min equaled 32 in our original case. Now min equals 2. And you can write all this stuff out on the whiteboard when you're testing this. And it's really helpful because if you're having trouble keeping track of this, so is your interviewer. And if you're having trouble keeping track of this, it's easier for me, but I'm struggling too. So definitely write everything out because it just makes it a lot easier. So now we have x equals 2, which is not equal to 0, min equals 2, and then we're going to come down to here, and x minus 25, 10, and 5 are all negative. So x minus 1, we're going to call change on x minus 1, which is 1. So now we have x equals 1, and min is also going to be equal to 1. So we're going to come one more time, or two more times, and we're going to say it's not equal to 0, and min is equal to 1. And so we're going to come to here, and the only coin that's smaller than or equal to 1 is 1. So we're going to come and we're going to call change of 0. So now x equals 0. So we're going to return back 0. And now we're in this loop where x was equal to 1 and min was equal to 1. So now this is going to return 0. And then so min is equal to 1 and min is equal to 1, and c plus 1 is 0 plus 1 is not less than or equal to 1. So we're going to just keep the 1. And so now min is equal to 1, and we're going to return 1. So now we're going up our stack again. So we're x equals 2 and min equals 2 now. So change is going to return, this returns 1 here. So now we have c equals 1, and if min is greater than c plus 1, so if 2 is less than 2, which it's not, so we're just going to return min here. So now we're going to go up one more, and we're going to say now c equals 2, and min equals 7, and x equals 7. So we're going to come down to here. So c equals 2, and now min is 7 and c plus 1 is 3. So we're going to say now min is equal to 3. So min is equal to 3, and then we're going to return min up one level. So that means that now, and I should note that I'm skipping some steps along the way because I didn't want to go through all of, obviously in this case with min equals 7 and x equals 7, it's also going to go through all the cases where coin is equal to 1, or right, where coin is equal to 1. So you're going to end up with a version where you get 7 coins, and we know that that's there, and that would run because it's the way that the recursion is set up, but I'm going to skip that because it takes too long and I don't want to go through it all, and your interviewer will totally understand if you don't want to go through it all either. So now we're coming back to 32, and this is going to be the case for all of these layers. I'm going to skip all the extra, but you can go through more of it if you want on your own time, just for practice or whatever. So now change returns 3. So c equals 3 here. And now min is 32 and c plus 1 is 4. So min is now going to be equal to 4. And now we're going to return min. And so our result is 4. So now we get change of 32 equals 4. And so logically, we can if we think about this, we know that that's correct because we get 25 cents, 5 cents, and 2 pennies. So we can say, we could test this more, but again, it probably works for all intents and purposes. So I'm pretty happy with the way it is right now. So at the beginning, I mentioned that this is not really an optimal solution, and it's pretty easy to see that that's the case because let's look at our example of change of 32. So in this example, you're going to be calling change of 1 32 times, and you're going to be calling change of 2 16 times, and you're going to be calling change of 3 8 times or more or less, and you're going to build up this tree of recursive calls down, and you're trying out every possibility. So you're going to end up with a quadratic runtime, and that's really not great. So we can actually And part of the interesting part of this problem is that we're going to be able to speed this up pretty quickly using dynamic programming technique. So if you don't know what that is, you should read up on it a little. But the idea is that we're going to cache the intermediate values that we're getting from our recursive calls, so we don't have to keep doing the recursive calls over and over. We're only going to have to make each recursive call once, and this is going to give us a linear runtime because you're only calling for example, you're calling, if you call change of 32, you're going to call change of 32 once, you're going to call change of 31 once, and each time you call each successively smaller amount of change, it's going to cache that value. So you're going to call change of 1 once, and then every future time you're just going to look up that value that you've already computed. So in this case, we can actually do it fairly easily, but it's going to take a little bit of reconfiguring of our code. So I'm going to start, what I want to do is I'm going to make an array that's going to be X long, and that's going to be a good enough cache because that's going to be able to store at index I. I'm going to store the value of change of I, and I'm going to do that for all values. Or I'm going to do that for all values that I hit through my recursion. So I'm going to go ahead, and I'm actually in Java. This is pretty simple because I can just overload the function change. So I'm going to actually call this one, I'm going to do int x and int coins, and to make this work properly, I'm going to overload it. So I'm going to add another int array, and this is going to be the cache. And so I just want to create the cache in my main. So when I call change, I'm going to call this first method, and this first method is going to call into my second method. So I'm going to create a cache, and I'm going to call it cache, and I'm going to make it X long. And now what I want to do is it's going to initialize all the values to 0, and that's a little bit tricky because I want the value of the set value of cache item 0 is actually supposed to be 0. So it's hard for me to differentiate between set and non-set cells. So I'm going to go ahead and initialize all of the values to -1 because I know that I don't want any values of -1. So I'm just going to do for I equals 1, I is less than X, then I plus plus, and cache I equals -1. And as you can tell, I am maintaining the 0 in the first cell because that's the right value, and it'll just be slightly easier for my algorithm if I do that, but it doesn't really matter too much. And now I'm just going to return change of X coins cache, and I now have to make a few changes to the rest of my code. So I'm going to go ahead and let me see here. I want to, so I'm going to first, actually, I'm going to check in here whether or not my value is already in the cache. So I'm going to just set int, I'm going to create an int c, and now I'm going to do if cache of x minus coin is greater than or equal to 0, because that will mean that it's already been set. Then I'm just going to say c equals cache of x minus coin. And that's pretty simple. And then otherwise, I'm going to calculate it, and then I'm going to I'm going to calculate change of x minus coin, and then I'm going to save it in the array. So I'm going to do c equals change of x minus coins, and cache. And now I'm going to say cache of x minus coin is equal to c. And that is that. And then I'm going to, I no longer need this line here, but I do still want to figure out which the minimum value is. So I'm going to keep this, and I'm going to return min at the end. And that's really all there is to it. And I'm going to leave this for you to test on your own because I think this video has been long enough already. But that's the minimum change problem, and there's a lot of stuff in there, so hopefully that was helpful to you. And I will see you again soon.